Hi, I'd like to welcome all of you to today's webinar for Adapt Builder. My name is Spencer Lee. I'll be conducting, the webinar today. The webinar will be recorded, so we will add the recording to our YouTube channel, which is youtube.com/adaptsupport, and there's a playlist there labeled Adapt Webinars, so you can go back and rewatch at your convenience or share with others that might be interested. Just a few announcements. If you have any questions during the webinar, towards the end of the webinar, we will spend a few minutes just answering questions related to the content. And if you have questions during the flow of the webinar, we'll try to answer those as well. You can just type in the question in the question field, and typically I'll be able to see those appear on my screen, and we'll stop and answer those. If there are specific validation questions, I would just ask we can save those for outside of the webinar. You can always email us or contact us at support@adaptsoft.com, and we'll be happy to answer those as needed. Also, if you have any other unrelated support questions that may not apply to today's content, then please just send those also to support@adaptsoft.com. We'd be happy again to answer those in that format. So again, I appreciate everyone being here. Today we're going to talk about exploring design of mat slabs, or really in general just foundation systems that can be modeled as an integrated integrated with multi-story structure. And this could be a podium slab with footings or foundations. It could be, what you see on screen, which is 10 or 12 stories. It could be something even larger, more complex, less complex. We really want to just make sure that everyone understands the integrated approach that can be used when evaluating multi-story structure with the foundation in the same instance. And it's important to note one very small detail. You'll notice today that I have the program opened in Adapt Floor Pro versus Adapt Mat. And so I'll describe the difference. There's a couple of differences there in how the program handles the ability to apply reactions at the base level when you have Adapt Floor Pro or Adapt Mat turned on or activated in conjunction with Adapt Edge. So also the workflows that we're going to discuss today will include both use of the tributary load takedown tool, which is specific to gravity loads, as well as the global finite element solution. And I'll reference global solution in the same context, the same terminology for if I reference full structure or multi-level global. Those all mean the same thing. It just means we're running the program in a mode that considers all of the components that are currently modeled in the model. So we'll go ahead and start by just describing some of the geometry for this model and just some of the input for the model, so we get our bearings as to what we're actually going to be evaluating. And I'll go ahead and turn off the shaded view. I'll just go back to wireframe. We have, I believe it's a 10-story structure with columns, shear walls. At the base of the structure, I'm going to switch over here to single level, and you can see the active level is currently the mat level. So at the base of the structure, we have a mat slab. And if I go into a plan view of this mat, the mat slab is 24 inches thick. We have a compression area spring with some subgrade values, subgrade moduli values here for the vertical and the lateral directions. And our purpose really is to show how do we get reactions onto that mat? How do we evaluate the mat for purposes of looking maybe at soil pressure, displacements, and just design of the mat for strength, for factored level forces. And in other programs and even previous versions of Adapt, this was unavailable to a user. You might have to generate a solution that includes both gravity or lateral forces from a general frame program, and then somehow extract those reactions and either manually apply the reactions onto another in another program in order to design the foundation. And that by manual, that could be literally just graphically entering loads, reactions for multiple load cases or combinations, and that can be time consuming. So the workflow we're describing today, I think, will really show and display how this truly is an integrated approach, and it's an efficient approach to being able to handle that type of solution. So we have our map level here. If I navigate up floor by floor, you can see we just have a few elevated floors. These could be post-tensioned, or they could be just RC, or you could have a combination of both. In this case, we don't have any post-tensioning, so this is just an RC two-way slab. And if you do include post-tensioning, the program inherently considers the secondary reactions and their effect on the global frame analysis, as well as the reactions that are applied down at the base level. So that's something that is unique about the DAP's solution here in Adapt Builder. We have several floors of this kind of floor plan, and it's just a repeating pattern, and then we get into a situation where the floor plan changes, and we have a couple of transfer columns here that are dumping load into this wall below. So that's one unique thing that that we can look at when we generate the tributary loads. And if I just navigate up, we have at the very top, we just have some elevator override slab. So this is our global structure. Material strength and things like that, those are defined here in concrete, and steel materials and pre-stressing. If we have pre-stressing, I think the concrete here is pretty simple. It's just slabs are 5,000, everything else is 6,000. And one other thing we want to make sure we note is, for this particular model, we have multiple usage cases defined. And what a usage case is when we analyze the structure globally or in single level mode, we can apply a set of stiffness modifiers to the components that are being evaluated during that particular run. So if I just double click on any component, for example, I'll just double click on a column, and I go here to stiffness modifiers, you can see that the uncracked usage case is the default case. It's always 1 for these different entries for moment or axial. We've added 2 additional usage cases, 1 for lateral and also 1 for gravity. And you can see the lateral flexural stiffness has been modified for columns to 0.01. So we're just trying to release the columns from participating laterally when we run this using the lateral usage case. And then for gravity, we have some other modification set. These are just arbitrary values. We're not meaning to have these intended to be code-driven values, but these are just entries for factors that are applied to our stiffness entries for the components. So every component in the slab, or every component in the model rather, has an assigned factor for lateral and gravity usage cases. If we wanted to add an additional usage case, we could always come here and just add an additional. I could write in, another, maybe this is a strength usage case, and then we could assign factors to components and assign them to that particular usage case. So the program will store solutions for every usage case that we run. And I've already, prior to the meeting today, the webinar, I've run finite element solutions for each one of these usage cases. So sitting off in the background somewhere on your machine where we store this solution, we already have in place a solution for uncracked, lateral, and gravity usage cases, meaning I could extract and use the reactions for any of those usage case sets when I reapply them to the foundation. So prerequisite to being able to apply the finite element solution reactions, you have to run the model using finite elements. And we'll do that, we'll redo that for uncracked, but I have the other 2 already stored. How can you tell if they're stored, or how can we remove the reactions? How can we reset reactions in the program? Well, if we go to FEM and go down here to Reaction Manager, this shows me which reactions are currently saved. So for each load case, dead load, EQX, EQY, hyperstatic, live load, etc., the program shows us which reactions have been stored. And this is showing us that for dead load, we have a gravity reaction made from a global run. That means we ran the model in global mode, full structure, and we used the gravity usage case when we ran the model. So this gives you an accounting of the different reactions that are currently available for you to reapply. And the reapplication of reactions doesn't always need to be at a foundation level or a mat level. It could be at a transfer level. If I had a level in this model that was containing some transfer slabs and or beams, we could reapply reactions to that particular transfer level. The same workflow is used between a transfer level and, let's say, a foundation level, but there's a few minor differences just analytically with how that's done, mainly the fact that at the foundation level we have a spring versus an elevated level. If I go to single level mode, and I'll just navigate down here, we'll say that maybe this level is a transfer. When I run this level, there's no spring. We're assuming that the base is fixed in the Z direction for a rerun of a single level that's elevated. So that defines usage cases. If we were to run the model using FEM, and we go to FEM and we analyze the structure, you can see that when we analyze the structure, we have the ability to select which usage case we want to use for that particular run. So we'll go back and we'll run uncracked, but before we do that, we want to talk about tributary loads. So in this model, we have the ability to apply reactions at the base level in two different ways. And I'll make a little drawing here on the side so we can try to explain this. We have our mat and our structure, and in one case we're going to use tributary load takedown, we call it. This only applies to gravity. In the other case, we're using FEM, and this might apply to both gravity and lateral. Clearly, if you want the ability to apply moments at the base, at the mat foundation, you must run this in FEM, because this only applies to axial load takedown for columns and walls. So the nice thing about this is when we do this method and we get reactions down at the base, or we do this method and we get reactions, we might get shear and we might get moments at the base in these columns or walls. We have the ability to decide or to envelope which reactions we want to use and apply to this base. So the first thing we have to do is we have to generate tributary load takedown, and we have to run the model globally to obtain a solution. And like I said earlier, we've already done that for 3 different usage cases. Once that is done, we transition here to single level mode, and then we have our set of reactions that are internally applied to this mat, which is on springs. So when we go into single level mode, we have the ability to tell the program use these reactions either from tributary or from FEM, or combine them and envelope them. One other important detail here is how do we assume the base of the structure when we have a spring? Because this spring is in place. You can see the spring is, I'm kind of highlighting that spring. It's there whether you run the model in single level mode, which is here, or whether you run the model in global mode, which is up here. So you have springs. The question is whether you want to consider the springs for the global run. So you have this difference between what we call a direct solution with springs or a indirect solution where we substitute the springs with a fixed support, and then we solve that problem, and then we come down here and we apply the reactions, and we'll go through both workflows. So this is kind of what we're going to lay out in terms of loading. I'll go ahead and erase that. Bring this back over. And under loading and load case library, we have just some basic loads here. We have dead load, which is the superimposed dead load. The program will auto-calculate the self-weight. We have live load. Again, it's unreduced. I think it's 40 PSF for all of the levels. And then we have building loads, which are lateral loads that will be applied to the structure. And the building loads we've defined are wind loads and earthquake or seismic loads. And we have those in two directions, essentially. So we have wind load applied as an external load, essentially in the global X direction, plus minus. And we have wind load applied this direction, plus minus. And we didn't go through all of the different load cases or the permutations that might be relevant, let's say, to ASCE 7. We have a handful of loads, but we're not going to apply all of those in this example. And then we have earthquake loads also in the X direction and the Y direction, and those include some torsion, I think 5% eccentricity based on the center of mass for each of the story forces. So we have our sets of lateral loads and gravity, and I'll go up here to load combinations. And in the combination list, we have 19 combos. Originally, this model had probably 300 combinations, but I really scaled it down just for the purpose of the webinar so we can run through the analysis fairly quickly. We have several strength combos and then several service. I think the two top combinations of each are gravity only, and then the remaining for strength and service contain a combination of wind or seismic. So we're combining the effects based on, I think these are based on ASCE 7 for the generation of the combinations that are used here. So we have our combination list. The next thing we're going to do is we're going to we're going to generate load takedown. So we haven't run a finite element solution yet, but we're going to just do a very basic check of the behavior of the model using load takedown. And so we'll go up here to loading, and we're going to go to tributary loads. The tributary load dialog will appear, and the program will geometrically define and determine the tributaries for every wall and column on each level by using this method. So we'll regenerate the tributaries, and you can see over here you get all these red regions that we'll look at those in a moment, and then we'll recalculate the loads for the tributaries. And we have some settings here with how the program interprets intersecting walls and columns and tolerances. We'll leave those just as default. So the tributary generation is done. The tributary loads that the program calculates is done for each of the defined gravity loads that we just showed in the load case library. So in this case, we have self-weight, dead load, and live load. And I'll go ahead and say OK. And now let's just take this up to the top level. I'll go up here to level 10 and set that as my active level. And I'm going to open what's called the result display settings. So this graphically allows us to control what results we're looking at. And I'll go down to the bottom of this list under load takedown, shown right here. And I want to first turn on the tributary boundaries. And this just shows us graphically the region and which support belongs to that region. So I can click on these different supports. This tributary you see here, if I open up my highlighter, this is for this wall that we have right here. So all of this load gets sucked into that wall. All of this load is goes to this column, and so on. If I go to erase that, I'll go over here to tributary area. So this shows you the level area. If I navigate downward, this shows me level by level what the tributary area is. The tributary facade is really if it's an exterior column or wall or part of its tributary region is bound by a perimeter of a slab. This is the facade length that you see here. So if you have line load on that facade, it would account for that, as well as the uniform load or line loads or point loads that might be, in this region. The tributary loads, this will show me level by level what loads are taken into that support. So if I navigate downward, for example, this has 19.63 kips of dead, 11.6 live, and 26 kips of self-weight. If I go to the next level down, it's the same exact loads, because this is now showing it level by level versus cumulative. If I go back up to the top and I go to cumulative loads and cumulative area, then this will account for the accumulation of loads. And you see the sign changes. That's just that's due to how we're pulling the loads out of the back-end data file and just sign conventions. So in this case, the negative is compression, positive is tension when you're looking at cumulative loads. So this accounts for the loading stacking on that particular location. Now, the purpose of this is to have the ability to use a geometrically based load takedown method for the axial loads versus a stiffness-based finite element solution. And this becomes more critical when you have lots of multiple level structure with, let's say, differences from level to level in stiffness, or you have some transfer conditions that might cause strange redistribution of forces due to the finite element method. And this gives the user another way to extract the loads rather than relying solely on that approach. So what I'll do is go down to the base level. Notice we haven't, again, I haven't meshed the structure yet. It's actually meshed, but I haven't run the finite element solution at all at this point during the webinar. I'm going to navigate down to the base level, and I'm going to run the solution for the mat using only tributary loads. So this would be, let's say, workflow 1. And the order of the workflow is not the suggested or the recommended order. It's just the first example we'll look at. We'll go here to FEM, and I'm going to analyze this isolated mat inside of Floor Pro. So it's in single level mode. We're ignoring the rest of the structure other than the ability to introduce the reactions. So if I go over into this input, you can see I can select my load combinations that I want to evaluate. And I'm just going to select a couple here that include gravity only for the first run. You'll notice when I select combinations that includes gravity only, self-weight, dead load, and live load, the program filters out which reactions are actually available to the user to select. So if I grab one that includes this wind load case, in addition, that wind load now becomes available as a reaction. If I deselect it, deselect that and that, it goes away. So the program has an auto filter as to which load cases are available depending on your selection of combinations. When I run a mat in single level mode and there's a spring there, by default I have to have a spring, otherwise it would be unstable and you would get a error message. The program automatically considers the presence of the spring. So I'll pull my highlighter up. This automatically will be selected. You can't change that. It's going to consider the fact that there's a spring in place. The user has the ability to include lateral reactions. In this case, this is basically not applicable because I don't have any combination selected that includes a lateral load case, seismic or wind. And I can also include load takedown. So by including load takedown, I now have the ability to apply the vertical reaction for dead load, live load, and self-weight. And the solution that comes from, the reaction set that I'm going to use can either be gravity, and that gravity comes from a run or FEM based solution with the usage case gravity, or it can be done using tributary. So let me go back and erase my markup there. If I select dead load, I can change this to lateral. That's my other usage case. I can change it to tributary, which is what I just calculated. I generated the tributary loads. I can use uncracked, which is another usage case. Remember, I have 3 usage cases: uncracked, gravity, and lateral. And they're basically just different stiffness profiles for the structure that are all currently solved. Or I can envelope. So the program will take all 4 and it will say, what's the worst case axial load on this column? Use that axial load for the run of this particular mat. We're going to use tributary. That's what we decided to look at first. So I'll go over here and change this to tributary. And notice that the reactions are only axial because I've selected tributary. Even if I selected gravity, I only have, I guess, at my disposal the ability to apply vertical reactions for load takedown. Notice that this include gravity reactions is turned off. And that's one of the different nuances between having the program open in Floor Pro or having the program open in MAT. When we open the program in MAT, we have the ability to not only include the gravity the gravity vertical force, the FZ value, but we could also include moments that are induced by the gravity effects and also shear. So right now I only have the availability of using the vertical reactions. That's fine. We'll go ahead and run this with only vertical. My stiffness modifiers that I want to use for the rerun of a single level needs to be selected, so I'll just use the uncracked, and then we'll go ahead and analyze the mat in this case. So the program is processing a solution based on the tributary reactions, and we get a result, basically. I'll go up here and just take a couple notes. I'll use my service 1. I think this is total dead load. And you can see I can look at deflections. The deflection under tributary loads is 0.23. And if I wanted to look at soil pressure here is 3,275 PSF. So we're going to just take a few comparative notes between the different processes. If I wanted to change this unit, this is something that I think some users may not know that is available. If we go to settings, say set units for stress, I can change it from PSF to KSF or PSI, whatever you want to evaluate the pressure with. So that's the first run. These pressures that you see are the pressures due to tributary load takedown axial force only. And if we go in here to the model viewer, you can see that we get some deformed shape based on that applied load. Now, if you forget to actually include the reactions, that's something that also comes up quite often. If I go back to analyze and I forget to include the load takedown, it should be pretty clear that there's no reactions being applied, but sometimes, people miss that. It's kind of over here to the right-hand side, and I rerun it now, and we're expecting to see some, high displacements where we have this large core wall and maybe large point loads from columns. If we expect the result, you can see this now, the pressure is 420 PSF. And obviously it's lower because we're not applying any reactions. The only application of load on this mat is the self weight, and any applied gravity load that's applied at this level, like surface load, maybe some, just minimal live and dead load. So that's something to be careful of. Make sure you select the option to apply reactions. Okay, so that's workflow number 1. Now we're going to take this a step further, and I'm going to go back up to global mode, And let me go ahead and turn off those results. And I'm going to rerun this. I have a mesh in place. I'll turn the mesh on. I've already meshed the model. So this is my FEM. And I'm going to now reanalyze the global structure. And there's a little bit of a difference here we have to be careful of. In this case, I'm going to run a few combinations that also include lateral. Okay, so I select my combinations that I want to evaluate. I need to decide which stiffness modifier usage case I'm going to use. Well, I already have a solution for all three. I'll just rerun uncracked just for the sake of selecting one. And then the next thing that needs to be determined is how do we want to approach the analysis. Earlier I mentioned there's a direct solution when we run the model globally, and there's an indirect solution when we run the model globally. If we choose to use compression springs, that's the direct solution. I can assume that if I use my compression springs in the analysis, the entire structure is going to basically settle based on the stiffness of the soil in our input, and from that direct solution, you can explore the the pressures, the design of the mat, and so on. Or you can use the option for substitution. So this is the indirect solution. If you substitute the springs at the base with fixed supports, you have basically zero displacement at the bottom of the slab. And then in the indirect solution, you must go back to single level and again reapply the reactions like we just did for tributary. So those are two different approaches. We're going to do both. You might ask, well, what's the difference? Why would I ever choose the indirect solution for a model? The option to use compression springs is probably not as, let's say, as realistic as one would think, especially for a multi-story structure that's built sequentially. As you build the structure, the soil might displace, fractions of an inch or millimeters, and then it stabilizes. And then over time, you're going to get more movement. But as you continue to build and build and build, you get, sequential, let's say, displacements at the base of the structure. When you run the model in direct mode, I'll call it, or use the direct solution, the program just assumes everything instantly appears and it's all generated at the same time. So there's no instantaneous there's no sequential approach to the analysis. And so another reason you might use substitution is because the analysis just takes much shorter duration of time, especially if you have a lot of combinations. For when we use compression springs, each combination becomes its own solution. We have to solve it independent, and we can't use superposition of the load case solutions. When we run with substitution, we just obtain solutions for each load case, and we can combine them in the combination and produce a result. So you could potentially have a model that's quite large. You have maybe 100 combinations, just for example, and you run it with compression springs. You might have to start that model and wait a couple of hours for it to solve, or longer. Whereas with substitution, the indirect approach, you solve it in 1/10 of the time, and then you go directly to single level and reapply the reactions. So substitution is what's done, I think, in a lot of cases with structures where you assume it's fixed at the base, or you have zero, let's say you have an infinitely stiff vertical support, and then you take those reactions and reapply them for the design of a foundation. So we're going to run let's go ahead and run the substitution method first. And I'll run this for, let's see, 13 out of the 19 combinations. And remember, this is the uncracked solution. I already have the other two solutions in place, which are the gravity and then the lateral. And you might ask, well, why do we need to run it 3 times. What's the purpose of requiring multiple usage cases? Well, if you wanted to combine lateral and gravity effects, you might want to apply different multipliers to different load cases. So for gravity load cases, self-weight, dead and live, you might apply, a just arbitrary number, 0.7 to the vertical stiffness. But for lateral, you might apply a value that's lower than that. So for the lateral effects, let's say for wind and earthquake load cases. So you can combine solutions that stem from different stiffness cases into the same rerun of those reactions. That might be a reason why you would want to use multiple usage cases. So this is done. Now, if I take a look at I'm going to go over here to this results viewer. This is just another way to view the results. I think it's a little bit quicker and it responds faster too. So I'm going to look at the Z direction displacement for whatever the first combination is. It's strength 1. What I want you to notice here is the base of the structure is not moving. So the base is not moving, and all of the slabs are moving, obviously, because they're elevated. So this base is rigid. There's no deflection there. That's showing you that we use substitution of the springs. I'm now going to transition back to single level mode, and I'll go back to this mat level, and now I'll go to FEM, and we're going to again analyze the structure another time, and I'll analyze it just for the same set of combinations. So in this case, again, we're going to use compression springs since we're in single level mode, and at the base of the structure there's a spring there. There's an area spring. I'm going to include lateral reactions. Okay, so for EQX, I'm going to use my lateral solution case. For EQY, I'll use lateral. For wind, I'll use the same for wind P0 and wind P90. And it's applying all of the reactions, FZ, MX, MY, etc. And I'm also going to include load takedown. So here I have my dead, live, and self-weight. But in this case, I'm actually going to use the envelope of all of my FEM runs and my tributary run. So I can mix and match which reactions I'm actually pulling from and using. So I'll use envelope. And this is only applying the FZ force. This is applying all reactions. Remember, this FZ is only available if I'm in Floor Pro. If I'm in Adapt Mat, I can use include gravity reactions, which would give me all reactions at the base. So now I'm going to rerun, and I'll rerun again with uncracked. This will allow us to obtain a solution now considering the effects of both gravity and lateral load. So we'll go ahead and say OK. And if I just compare the service 1 deflection between this run and the previous run, actually let me compare the stress. I think this deflection is 0.26. The previous run was 0.23. If we go here to soil pressure, the previous run was 3275. This is 3750. And you obviously can go in and change this. You can evaluate, different combinations for pressure, for displacement. You can look at, bending moment contours, in plane axial contours. So there's a whole slew of different results you can get for the analysis. Here we're just kind of focusing on displacement and the soil pressure. So that is workflow number 2, which again is the indirect method where we substitute and then we go back and reapply reactions for the lateral and gravity effects. Okay, so we'll use strength 1 as our, let's say, gravity only comparison. So this is gravity, and then we're going to use, let's say, strength number 4, or excuse me, service 1 for gravity comparison, and we'll use service 4 for gravity and lateral, because we want to compare this to the direct solution as well. So I'll go down here to Z displacement at 0.24. This is service 4, service 1, and then the soil pressure again is 3466. Okay, the next thing we're going to do is we're going to go back to global mode. Let me just clear that. I'll go back over here to global mode. And now we're going to run the solution with springs. So we'll go to FEM. I'll analyze the structure. I'll use the same set of combinations that we used previous, but I'm going to use it with compression springs. So when I analyze globally with or without springs, all of this stuff basically becomes null. You can't apply it. They're just there visually, but there's no application of reactions in global mode. But we want to make sure we set this to compression springs. We're going to run this for uncracked again, and then we'll go back and obtain our solution here. If any of you have any questions, please let me know. I haven't seen any questions yet, but you certainly have the ability to ask questions during the meeting if you'd like. This may take a little bit longer, only because, again, we're obtaining solutions for each independent load combination. And once we've run this direct solution, then we're going to talk about just briefly about the design of the mat using these same types of solutions. So that will include the ability, the need for generating support lines, design strips, and evaluating those strips at either service and/or strength loading conditions. But the same general workflows can be applied not only to evaluating displacements or soil pressure, but also to evaluating or design of the mat slab for reinforcement. You can see this run has already taken probably just a few times longer than the substitution run, which was what we had mentioned earlier. Okay, there's a question. Let me just pull that open here. The question is, if we have piles, how can we design piles? We neglect the capacity of the soil and take only the capacity of the piles. If you have piles, there's a few things you can do. What I recommend with piles, you can model, let's say, long circular columns essentially as piles. So this essentially would become a pile cap at the first elevated floor, and then you model the piles, and the reaction of those columns in the model are your pile reactions. So you would remove the soil spring and you would add the pile, but then what happens there is that assumes the stiffness of the column based on its length and its properties. So you could try to adjust or calibrate the pile stiffness based on your input. Another option is to just eliminate the need for actually modeling columns, and you could put point springs at the pile locations underneath this mat in lieu of the area spring. And for the point springs, you could then adjust the stiffness for those springs in the model. So that's how you could simulate the pile modeling in the program. I think that's the is P delta available? Good question, Alexander. We are currently working on dynamic and P delta implementation in the program. It's not available right now, P big delta, but it will be available, I would say, by later end of third quarter of this year. The current project that is, I guess, occupying most of our time is we're building out a new user interface for the program, a new UI. So we're modernizing a UI to a ribbon-based UI, and our tentative release date for that is April of this year, so just in a couple of months. That will be builder 2018. The next question, what I know, adapt just gives you the contour displacements, not the exact value displacement in specific point. Yes, in other words, I can't scroll along the location of the location on a contour map and pull up the displacement. One thing that you can do, if you have a solution in place, for example, I could go to, I'll go back to that results viewer, and this is not ideal. I'll show it to you, but it may not be exactly what you want. But if you go, the displacements are calculated at node locations. So, you know, the contour is then created based on those nodal displacements. So if I go into this view, and in this case, I'll go down to the map level, and I can go, for example, Z direction translation. If I turn on the vector plot of the displacements, this is not a great view of this. This works, I think, better with, let's say, elevated slabs. But this would allow me to basically view the contours. This looks a little bit strange. It usually doesn't look. That's because we're at a mat is why. If I go, let me go to an elevated floor. Let me go up one level. I'll go to level 1, let's say. Okay, and if I look at the contour map, so we have some displacements here. At columns and walls, if I turn off the slab, for example, and I look at this frame element displacement diagram, this will give me frame displacement. So at the mid node, the top node, and lower node for each column or beam, you can get these point displacements. For the slab itself, what I was trying to show earlier at a mat, which I'm not as familiar with, is if you go to the vector plot, the vector plot should show you the values for displacement. It's just not turning on. I don't know why. Let me see if that was, yeah. So this will show you displacements at nodes, you know, at pinpoint locations, but it's at the locations of a node in the, you know, that we use for the mesh. So that's one thing you can look at and use if needed. Okay, I think that's all the questions right now. Let me go just check here. Is there any way to model drift show load? I think you're asking, is there any way to show drift, Alexander? I'm not sure what the exact question is, but you can clarify if you can. Oh, no, it says snow load. Okay, let me, no, you're asking, I think, snow load. Okay, that makes more sense. Is there any way to model drifting, like drifting snow loading? The answer currently is no. There's not. You can model trapezoidal area loads that might be a good thing to use. There's no explicit input, but you could, like, let's say right here where the floor plan changes, we might have a location where above along, like, say, this line, you have a step in the building, so you might get drifting on this roof, you know, right here. So what you could do is you could enter a trapezoidal area load. So if we go to loading, add load, patch load, if I go into patch load, you can either do you know, uniform magnitude, or you can do variable magnitude. And if you use variable magnitude, this allows you to enter triangular trapezoidal area loading on the structure. Okay, review the. All right, so kind of back to where we were there, where we were answering a few questions. We had just analyzed the model globally with the compression springs directly. So we're going to go back, and I'll go and view the displacement at the base now. Before I do that, let me turn on the results globally. So earlier we saw that the bottom of the structure was not displacing. Now we're going to see displacement at the base of the structure. I'll turn off the values, turn on the contours, and you can see this whole building is just sagging downward because the bottom is able to displace in this analysis run, which tends to pull the structure down, which induces additional forces and moments in the slabs above. So you'll actually get more displacement at slabs in this type of a run than you would in substitution, because the program accounts for that displacement and the instantaneous axial deformation in the columns as well. So those kind of build on each other and cause, I'll call it, magnified displacements or actions above. At the base level, we were comparing a few results here. So for gravity only, we said, okay, we're going to look at service 1. The previous run, the value was 0.24. This run, it's 0.24. And for service 4, we were going to check the soil pressure. So this is 3120. The previous run was 3466, and now we have 3122. So you can see along the path, we've done 4 different runs. We've done tributary axial only, was 3275. When we did when we did substitution, we had, let's say, 3466, and then the direct solution we have 3122. So I would not expect the same solution in each run, because we're changing the behavior, we're changing some modeling and analytical assumptions when we run each one of those unique solutions. Let's go now for the last few minutes here. I want to talk about the design of the mat for strength, or for just let's say reinforcement. So we have a solution. It's the direct solution. To get to this point where we want to design the slab, we could take any of those previous approaches and apply them. But here we're going to use just the last saved solution. So we'll clear this. We've run the model globally using the direct solution, and now I want to design the slab. So in this case, I've set up design strips, and if we look at my strips that I've set up, I have both X and Y column and middle strips. Let me turn off the... So here you have, for example, my X direction strips that I've modeled, and then obviously we have Y direction strips here. We're going to develop design cuts for each one of those strips. So we'll regenerate the tributaries. That shows me what the tributary regions are, and I can turn on the design cuts in either direction. I'll go to X or Y. So this allows me to display the design cuts, or to turn them off or on. When I turn them on, I get this switch that allows me to switch between X and Y. And now I can go ahead and directly design these sections for the solution that I just ran. So what I did, I just ran the direct solution. I'll just go ahead and evaluate a few of these support lines in the X direction. Actually, let me just do a couple because we're running short on time. I'll do this one and this one, and we'll go to FEM and design the sections. The same set of combinations that we evaluated during the analysis is what's being designed for. So we have 4 service combinations and then 4 strength combinations, and the program will produce a solution for reinforcement for each one of those combos. That's finished just for these 2 strips. Now if I go back and I go to FEM and I generate the rebar drawing, if I isolate this, for example, to service, we get some reinforcement for minimum. You can see this one looks kind of strange. Why does it look strange? Well, if you look at my X direction support line, it basically follows that path. So the program is extending these bars out due to there's a few different parameters in how the algorithm works for the bar placement, but part of it is associated with how the support line is laid out and where we have additional need for, let's say, minimum reinforcement at the top. If I wanted to straighten the bars out and make everything orthogonal, I could go back and just regenerate the same reinforcement. This was envelope service, and produce it based on its orientation relative to the X and Y axes. So I could rotate this. And now you say, well, now I have this blue rebar. What is this all about? Well, the blue rebar that we get, let me turn on the reinforcement toolbar. I'll display that again. The blue rebar means that the program tags it as that color because the bar either extends beyond the slab edge, so it extends into a different region, meaning it doesn't belong to the same region at every position along the length of the bar. So here you can see this bar is extending out of the slab, so it's basically a warning. It's an indication that, hey, something's going on here with this bar. You would also get this blue color where a bar might be located in two different thicknesses or multiple, let's say, multiple sections of a slab. So if we had a situation where we had a bar that went through a drop panel and extended from a slab into a drop panel, out of the drop panel, let's say at the top, the program might also, or excuse me, at the bottom, then the program would also flag that as this type of a condition. So this is what it's calculating for minimum rebar for these two strips, top and bottom, and I can isolate those bars if I wanted to show top only, or I could go back, regenerate it for the entire envelope of bars or envelope of strength or an individual combo. So this is what's required for strength. You can see it's actually piecing bars together. So you might have demand at certain locations for different combinations, but when I envelope it, it's just going to chain those bars together if they overlap individually, if we looked at the individual combos. So I'll go back here and I'll just pull up one strength combo, for example. We get something like this. So the program can produce those reinforcement results. If I had designed all the sections, then obviously we would have reinforcement for the entire mat. In this case, we've only produced it for two design strips. That will conclude today's session. I'll take 5 to 10 minutes to answer questions if we have any, but I appreciate everyone's participation today and your willingness to join us. We'll be adding this again to the YouTube channel, youtube.com/adaptsupport. And if you have any follow-up questions or need us to produce more explanation for any of the things we discussed, please just let us know. You can email us at support@adaptsoft.com. So I'll just wait here, and if you have questions, please feel free. Otherwise, thank you, and you can just exit the meeting at your leisure. Okay, Alexander, you asked, can we see the envelope of soil pressure? Yeah, let me go here and check that. The envelope of pressures is currently unavailable. For example, if I go up here to envelope, let's just do envelope of service, and let me see, where's soil pressure? There it is. So if I try to produce that, nothing is shown. That's an improvement request we've received by numerous clients. So right now you have to look at the pressures independently, but I would expect us to make that change sooner rather than later. The question is, there are many cases in ADAPT for calculating the rebar for strength combination, like over reinforced and under reinforced. Please explain. For the person that asked this question, I will send you a detailed technical note But just in general, there are 6 unique cases that the program will consider for designing a section for strength. Number 1 is if the capacity of the base section is, if it's less than the demand, the program will just simply add a reinforcement, and it will always also check ductility. So if the section has so much reinforcement, or if the calculated amount of reinforcement results in the ductility ratio, or the ductility threshold being exceeded, the program in some cases will either add, you could have a situation where it only adds tension rebar, which means that ductility is not exceeded. You could have a situation where the required amount of tension rebar it exceeds ductility, so then we have to add compression rebar in order to drive the neutral axis up and maintain the ductility. The whole premise to this is that ADAPT does not adjust for example, for ACI, we don't adjust the phi factor between compression and tension controlled sections. We always assume the section is tension controlled, and to impose that rule, we have to impose ductility on the section. So that's why it goes through these multiple checks and cases where it's checking the ductility. You might have a case where you have so much post-tensioning or so much base reinforcement, which is just user-defined rebar, that it's already over-reinforced. So now the program has to add compression rebar to drive, again, to move the neutral axis and maintain the ductility. So there's multiple cases. There's really 6 cases that it might go through. And again, I'll send you detailed information on each one of those. It's just numerically, it shows you what equations are being used and what material models look like and what those ratios are. Any other questions? Okay, if there's no more questions, we'll go ahead and conclude. Again, I appreciate it, and we'll look forward to seeing you guys soon. Thank you. Let me check this. Yeah, there is one more question. Hold on one second here. Any improvement for beam design? Yes, there are improvements in Q, Alexander, for beam design. We plan on adding a beam design manager inside of the program. Some of the framework is already there. For example, if I go up to beam type manager, the section manager, you can see the type that you can apply here. If I add a new section, this can be, where did that section go? Let me add one. So you can see we have beam type right here. So in essence, what we're going to add to the program is a beam manager where you can, the program will auto detect beams that you've modeled. The user can then input a flange width, or you can impose effective flange calculations per code. The finite element solution will be used for the forces in that beam, but the beam itself will be designed independently inside of that beam manager, as separate from the strip design for just the floor or the level that you're working on. So those improvements are in queue right now. The question is, how about a pile raft foundation? We must give spring, area, soil, and spring point, because we have to make sure that the reaction at spring point not exceeding the bearing capacity, and we have to make sure the contour displacements is the same as the geotech settlement calculation. So this is, I think what you're asking is, can we combine point springs with a different thickness or a different stiffness than area springs? The only way to do that, if you overlap a point spring and an area spring, the program will take the lesser of the two values and assign it to the node that the area spring is nearest. So if you want to mix the two, you have to use multiple area springs and point springs where you have the piles. So I couldn't create an entire area spring. I would have to in this example, I would have to, maybe add point springs where I have my piles. You can see I'm adding a few springs here. And in between those point springs, we could come back and add an area spring of different, let's say, of a different value. So I could piece together multiple area springs in different regions of the slab when I model the area spring. Okay, so there's a punching shear question. Do we check punching shear for columns located above a pile support if adapt gives me punching exceeds code? Yeah, if you have a series of pile, if this acts as a pile cap, essentially, do we check punching for the? Typically, the punching of a pile cap, the punching is made on the basis of you're checking punching for the reaction, not necessarily the support. So in that case, I would say it's critical for you to check that, but I don't think I would not, it would not be checked in adapt if you don't model the physical columns below the pile. Earlier I said you can either model piles as columns or you can model piles as point springs. If you model them as point springs, it won't check that punching. If you model them as actual physical components, then it would check the punching for the piles. And if it gives you exceeds code, that just means that the stress that the program calculates, the shear stress at that column that is calculated exceeds the maximum allowable shear stress for whatever code it is you're using. And you would either have to increase the concrete strength, you might have to increase the concrete depth so that you drive up the allowable capacity of the concrete, or if you used a pile that had less bearing capacity, which may not be the answer, but I'm just throwing out ideas. If you used a pile that had less bearing capacity, then you would limit the amount of stress that could be imposed on the slab based on that pile size. So let me see if there's any other questions in queue here. Yeah, there's a pile below the column. I realize that. I just mentioned that if you wanted to model that condition, let me just turn on the, I'll draw this here. Oh, that's not. Okay, so you have let's say this is a pile cap, and in the program you have a column that stacks on this cap, and then underneath the column you have several piles. So in order to check the punching for this, the punching is typically checked based on let's say the pile reacting against this cap, not necessarily this thing pushing down on it probably should be checked for both, but in order to get the check made for these piles punching through the cap, let's say, you must model these as physical components in the program. And then, so this, in essence, this does not become, you don't have a spring in this case, you have multiple components below this level. So this would actually be the first elevated floor. This is floor 1, and then the base would be down here, and these piles are just modeled all the way down to the base, wherever you reference the base from. Can we define, or can we provide user-defined rebar in a beam? Yes, you can. You just have to be mindful of how the program, how we reference the cover. So I'll go up to a level up here. Let's just go to an elevated floor. And let's say I add a beam along here. And this beam we're going to say is 30 inches deep. And what I'll do is just isolate the slab and the beam. So I'll select those and I'll isolate. And I look at this. And I have this beam underneath the slab. And my objective is to add bottom rebar to that beam. So if I use the reinforcement toolbar, I can add what's called banded reinforcement. And if I add my banded bars, I say, okay, I'm going to put three number 9 bars in the bottom of this beam. I'll change this to 9. I'll change this to 3. I can adjust the length or the material. And my cover is 1 inch. I'll say it's 2 inches. So my thought might be, well, that bar is referencing, the cover is referencing the bottom of the beam. But in reality, if I turn this back to a side view, the rebar input always references the slab. So you see this beam is, this bar is actually 2 inches above the slab. It's not where I think it is. So if I take that and I offset this by, let's say, negative 16 inches, then I push it down into the beam. So you have to input a negative cover for the bar to be in the beam. Are you going to have an option, a future option for a PT design of a mat? Eric, the program allows you to model PT at a mat. If I'm confused here, I don't know if that's the question, but if I wanted to add post-tensioning to the mat, I certainly could. In fact, if I go back down to the mat, if I open the program and adapt mat, or excuse me, in adapt, let's say PT and RC scope. In fact, let me close this and show you what I'm referring to. If I go to open the program and then make sure this is set to RC and PT, I have the ability now to model post-tensioning in any of the floors. It could be an elevated floor or it could be the mat. So I'll go back down to my mat level, and now, you know, if I go back to my, if I turn on my design strips in this direction, let's say I want to map tendons to this set of strips. I'll just select all of my support lines. I can use my tendon toolbar, and I'm just going to map tendons to these support lines. So I just added PT to this mat in the X direction. There are the cables that I've added. So you certainly can model post-tensioning in mats in the program. Okay, I think we'll stop there. If there are any more questions I didn't cover, I apologize. I have a very small window where I can see the questions, but let me know. You can email us again or give us a call. We'd be happy to help out, and I appreciate everyone's interest, and we'll talk to you soon. Thank you.